Okay, so it's 3 o'clock. Let's start the ASE seminar. Welcome to the 43rd ASE seminar, Advanced Supercomputing Environment. So I just briefly start from the history of this meeting. This meeting was started by Professor Takahiro Katagiri, so my former colleague. He's now in Nagoya University, so both of you are visiting him tomorrow. And so we started March 2008. So this is an irregular meeting, and we host this meeting when we have domestic and international visitors to our centers. Okay, and official language is not fixed. So yeah, today is English, and the first seminar was on March 3rd, 2008. And we accept any topics related to HPC and supercomputing. And the last meeting before COVID-19 was the 40th on February 4th in 2020. And the 41st was online last year, February 4th. And the last one is the 42nd. It's a hybrid meeting here in the April 11 this year. So today we have it's our great honor to have two excellent guest speakers. One is Dr. Elaine Rainbow from Sandia National Lab, and another speaker is Dr. Otsuni Marquez from Lawrence Berkeley National Laboratory. So both of them are visiting Japan for ECM 2023. It was held last week in Waseda University. It's the 10th International Congress on Industrial and Applied Mathematics. And welcome to Japan. Okay, so I'd like to briefly introduce both speakers before their talks. First, our speaker is Dr. Elaine Rainbow. She is a principal member of the technical staff, statistics and human systems group, applied cognitive science in the Applied Information Science Center at Sandia National Laboratories. So she's a social scientist. Okay? And so according to her CV, so her expertise is the future of the remote work, virtual teams, immersive virtual environments, and transmedia learning, methods for software productivity, and scientific visualization. So they are very interesting. So actually, so she hosted, organized a panel strategy for working remotely in SC21 2 years ago. And so I was, so this is some Zoom meeting at that panel, and I was one of the panel member there. So this is a very nice meeting. And so this is our first real meeting, so this time. Okay. And she's also a Sandia National Lab institutional PI for the Department of Energy Exascale Computing Project, ECP, and interoperable design of the extreme scale application software ideas. And I believe her talk is related to some software collaboration in this project. Okay. And the next speaker is Dr. Otsuni Marquez. He's a staff scientist, Scalable Solvers Group, and Computational Research Divisions, and Lawrence Berkeley National Laboratory. So he's my friend in recent more than 20 years. Okay. So. And so his expertise is HPC and numerical linear algebra and eigenvalue problems, and both for the engineering and the physics. And so he's one of the very important role for the LayPack or ScalarPack library. And he's also involved exascale computing project in DOE. And I think so his activity is also mentioned in Elaine's talk. Okay. And he was a program co-chair of the HPC Asia 2022, so where I was a general chair. Okay. So actually, this is the 6th appearance in ASM seminar by Otsuni. And you can see the first one is held for when he visited the University of Tokyo. Okay. So
true.
Actually, it's 15 years ago. Okay. And welcome back. And yeah, it's a very great pleasure to host both of you. Okay, so let's start the first talk by Elaine. So Are you ready?
ありがとうございます。ごめんなさい。私日本語ちょっとだけ。So I will give my presentation in English. I would like to thank Professor Nakajima for inviting me. I'm very honored to present in this seminar. And so I thank you very much for your attendance online and your attendance in person. I'm very honored to be here. So my presentation is about the socio-technical aspects of code collaborations. And normally I include a slide that explains my work, but I had such a nice introduction. I don't think I need to spend much time on this slide at all, except to say that the type of work that a social scientist does with other scientists is looking at collaboration and being embedded in the teams. And so you can see my image here is of an aquarium where fish swim together, a school of fish, and sometimes there is a fish that is with the other fish. It looks a little bit like the fish, but not completely. And that's usually me. I'm usually that person. But I like to be part of code teams, part of other scientific teams and other domains, and we work together. And I have had the opportunity to work in teams in Europe. I spent 2 years in Germany with Fraunhofer, 6 months in England with British Telecom, and a few months in France with INRIA. So this is the type of work that I do. I learn about teams and we work together to improve their software productivity. So when I speak about socio-technical, the way that I'm defining it is looking at actually how technology and society are very intertwined. It's my perspective and my belief that actually they influence and they change each other. So when we innovate, we have to think about the impact of our innovations on society and society's impact on our innovations. And so I look for these intended consequences and unintended consequences. This is how I help other teams, code teams and scientific teams. Also for me, a team is a team that has a shared or common goal. And so you don't have to be physically co-located to be a team. You can actually be distributed and still be a team. What makes a team work is a shared goal, a common goal, where you rely on each other for expertise. So in terms of collaboration, I would like us to think about, to explore this idea, to reflect. What are the different ways that scientific code collaborations start and how are they sustained? How do we maintain the relationships that we build with in code collaborations? And what are the challenges? This will be the emphasis of my talk. So now I'm going to move to a section where we're going to speak a little bit about the challenges of software teams and also what some of the environmental drivers are that might drive some of the challenges and some of the solutions to the challenges. And I hope that you can apply the information, perhaps think about your own teams or your own challenges. And if you would like to ask me any questions, I'm happy to answer them. So one of the things that I like to say about science is that, especially computational science, this is a very exciting time to be developing, and it is also a terrifying time. I love this quote by Eric Draeger from Lawrence Livermore National Laboratory. This was a comment he made at an Institute for Pure and Applied Math, where I was a participant in a program that lasted 14 weeks, where scientists, mathematicians, and computer scientists and social science, myself, we collaborated together. And so in his presentation, he really made this point that this is, in fact, if you like to innovate, this is a great time to be doing computational science, because more time now is spent on software than ever before. And increasingly, our projects are multi-institutional and they are very complex. And so because of the complexity, we are actually seeing that we have to keep up the pace, and it is very difficult. Many of our practices can't keep up with the pace of complexity. And so the demand for software is becoming much greater. And we noticed this in an earlier presentation today to introduce us to the University of Tokyo Information Technology Center. And so because I work with scientists, we have a tendency to show our slides and we talk about our software and our code. And this is a very common type of slide. This is actually an illustration of a code called Cabana, which is a portability code. And this was shown by Tim German, who is from Los Alamos National Laboratory. And I just wanted to show this because when I look at this slide, what I see are teams. I see many different teams who either might be co-located or distributed, who are working together to make this Cabana code a success. And so I see the people, for example, in HDF5, that is a team that I have worked with to improve their code productivity. And I see other teams from Los Alamos National Laboratory, there's COCOS. And so each of these representations really signifies the number of people involved in this type of work. And so because there are so many people involved, we do have many socio-technical challenges of scientific software development. You know, the technical challenges for scientific software development are that, first of all, the code is very heterogeneous. So GPUs and CPUs, and each part of that ecosystem can be under research at the same time, which means the software and the architecture is always evolving. That's why the requirements might change as we see the life cycle of the code and the ecosystem and our knowledge growing at that time. Also, there's really an importance now to have good reproducibility, good sustainability of code because of the changes or the complexities in the ecosystem. Verification is always complicated, and actually the world is a messy place, and so is our software consequently. Many systems, many parts of it under research at the same time. If we look at our social challenges, they're equally complex. We have challenges such as competing priorities and incentives, different motivations in order to complete the code or write code. Many teams work under limited resources. There's a perception that among some research software scientists that I have heard speak in other domains, other conferences, that there's a perception sometimes of invisible work, of all of the work it takes to maintain code, and not being really as important as a scientific result. We need more interdisciplinary interactions so that we can learn from each other. And then we have a great innovation in small teams, and we have to learn how to scale that innovation from a small team to a large team. Some of the environmental drivers that really influence our code collaboration can be that funding, when we write proposals to develop software for scientific codes, usually the funding is focused on our results. And often in the United States, there is an oversight to not include funding for actually maintaining code. And so the other aspect is that funding is also very competitive. Many teams say that they don't have time to write in software features that would make the code better because those features don't focus on results. And so the refactoring releases are infrequent. There's also a perception in the United States that software process improvement is a very heavyweight activity, that it takes a lot of time and effort. But in fact, we'll talk about some informal methods today. And there is some concern that we can't delay our scientific activities, and that if we have to take time to refactor or maintain code, that will impede that process. And then finally, communication between and across code teams is actually very complex, requires a lot of different technologies to have good communication. And so the point I want to make here is that science through computing actually is only as good as the software that produces it. So that is why the code collaboration is so important, and why it is so critical that in the sciences that we focus on having good software productivity and on our collaboration. And so I have as an example a story about a small team that innovated, and now we're going to look at how small teams and their innovations must be scaled to a large organizations. And what we have been doing in the exascale computing project is we have been thinking about this in the terms of teams of teams. So remember, I mentioned that a team was any group of people working on a common goal. Well, a team of teams is a larger umbrella of many key teams working toward a common goal together. So here's an example of just a small team. This is actually an example from my colleagues in Los Alamos National Laboratory. And I would like to acknowledge David Moulton. David Moulton participated in this project where, very 25 years ago plus, actually, his small team built Avalon, which was the first Linux cluster to break the top 500 supercomputer list. And it was a very small team, just a few people, but they were able to demonstrate that their application to molecular dynamics simulations was actually a Gordon Bell entry. And so we know that small teams innovate. Now, the challenge we have is how can we scale that innovation? And so this idea of a mythical programmer or the hero programmer, that one person that does everything, that is an idea that actually is becoming less, I would say less pervasive, because we see that it takes many programmers to make something really work. And so if you have a small team right now, or you are part of a small team and it's working really well, then you know that this innovation is really great. Small teams don't have to necessarily document code as much, because they can communicate quickly in their small team. They can share ideas, and before you know it, your idea produces a result. And so what makes this small team effective is the fact that because they are small and they know each other, they probably have a lot of trust, they have a common purpose, they have a shared knowledge or consciousness, and they have some sort of autonomy. So the challenge is how to scale that. So this is the idea that we've been talking about here, is moving from a few to few toward many to many. And this is an idea of communication. So if we look at the way we can communicate in small groups of people, few people speaking, or we can think about mass communication, which is communicating to many people at once. And so here, communication technology can really help us to communicate many to many. So in the first diagram to your left, you see a typical diagram of a hierarchy of an organization. And hierarchies are actually very good because there's efficiency in hierarchy, and there are roles in the organizations that everybody knows whose role it is, and that can be very effective. A network organization, which is over on the right, can also be very effective because these networks are usually very agile and adaptable, and this can be well suited. This type of communication can be well suited for an uncertain environment. So a network environment might mean that you go to the person that you know has information that is suited for that particular problem, and that may change. And so in that way, it adapts. The diagram in the center is the hybrid. This is the combination of a hierarchy plus a network. And here, a hybrid brings adaptability and resilience of networks to established organizations. And I'm going to show you an example. So the exascale computing project is actually a very large project. Dr. Marcus will speak about this later. What I want to focus here is that this project has 3 technical foci, and it has actually 6 core Department of Energy laboratories that are working together, but it has staff from most of the 17 Department of Energy national laboratories taking part in this 7-year project. And because we have 17 Department of Energy laboratories participating, we have 81 R&D teams, and that's approximately 10 researchers per team. And if you think about it, that's over 1,000 researchers working in this project and hundreds of milestones. And so it's a very complex organization, and with relatively small teams working together. And so here is a diagram that may not be very different from the ways that your organizations might look. So clearly, the exascale computing project is a hierarchy. We have a hierarchy in the organization. On the other hand, over towards the right, we have a network. And this is actually a very old cartoon, I would say, at this point, of some of our codes, the ECP codes, and how they might be networked together. And so the idea here is that we have a hierarchy of humans and human organizations, and we have code bases that are connected to other code bases. That means that teams are connected to other teams. And in the center, what's making all of this work together is this idea of team of teams. So one concept I would like to propose here is that sometimes collaboration is formed by humans. Humans want to work together. But sometimes collaborations are formed because of software. If your software is dependent on other software, that creates a collaboration opportunity that you may not have had if your code were not dependent on another code, or if you were not using another system. And so this is the proposal that I have for you today, that we can think about how our collaborations start. Maybe our collaborations start because a small code team, the user base grows, and now suddenly they have other users from other codes, and that is a point of collaboration. And so when you have that opportunity, when your code touches another code, or your code becomes dependent on another code, or maybe someone else is dependent on your code, what we can try to cultivate are some ideas of having a common goal, an aligning narrative. And so team of teams is actually a concept that was first introduced in popular literature by retired Army General Stanley McChrystal. And this was a term he used to describe how his organization worked together. And what he talked about was several key ingredients. For example, having a mission or a goal that you can each know that is common and that you are trying to achieve together. Being able to execute on that goal. So being able to knowing what you want to do and making sure everybody else knows it and you work towards it together. Also, having members of different teams working together, or at least talking about common challenges and common uh, goals that they may have. And then in terms of leading, it's important to remember that it's an ecosystem. And so it's not like a chessboard where you might move one chess piece strategically. It's more like a garden where you have to really cultivate and grow the different parts of the ecosystem, refactoring in certain places and innovating in others. And so we applied this actually to a project at Los Alamos National Laboratory. And here I will acknowledge my colleague, Amy Hungerfeld, who at the time was the PI of this advanced scientific computing project called RESTRA. And part of what her challenge was when she became the lead of this team, she had already some existing components that she and her team needed to put together. And so her challenge was, how to do this when you have a vision that you want to support the different scientific applications and compute architectures. So one thing that she did, these are the challenges she had as a new lead. Her code team was inherited from existing teams. So she had to work with people who were already on existing teams, and then suddenly they were part of a new team. And that included academic researchers, and it also included production support and development. So already in that one team, there were different cultures. She also had the difference in coding styles. They had different vocabulary. Their reporting requirements were different. They had different perspectives towards communication, and their software development environments were completely different. So this was a very difficult situation for her because everything was really new and everyone had already existing ways of doing things. So, how would she, change this? And, in some of her past efforts, the initial conditions mostly failed. So historically, these types of projects never really work. So one of the things she did was she started to think about culturally, how can she change this particular team? And one of the things she found being very, very important was unstructured collaboration time. So earlier today, I heard about a hackathon, and I heard about how the hackathon was started during the pandemic, and it was, or before the pandemic, and then it went online, and it has been continued. And so what's great about a hackathon is that hackathons also provide this unstructured time to meet together and talk. And so this turns out to be very, very important for people to just share ideas. Also, what's also important is to balance the team with expertise and experience from different ages. So it can be seniors and juniors. Also, getting management support to kick off teams that are coming together for the first time can be very important. And as far as technical tools, what they really had to do was they had to be very thoughtful about how they were going to collaborate. They started using the same tools together. They used the Atlassian development tool set. They had tutorials to learn how to use these tools. They started using Docker containers. So they had to be thoughtful about the tools and about the ways that they collaborate in person or online. And so this image here that where it says where there's tea, there's hope. This is actually a technique that is used. It's called tea time. So for unstructured collaboration, having actually a time maybe before a seminar where you offer food, where people can just come and talk informally, that turns out to be very important. People like to make good relationships that way. And it can help. That's why I think hackathons are so critical and why conferences are also very useful for this type of collaboration. So now when we think about remote work in particular, and I wanted to mention this because this is a hybrid meeting and because the teams that I have heard about today in the center are hybrid teams, or they are teams from different domains. And so you may have a situation where some of your teams are fully dispersed, meaning that they are remote completely. You may have another situation in the center, which is subgroups. And here we have, for example, it can be one building where we have people in one building, or it can be a floor of a building where we have people on the same floor. And then the last is hybrid. Here is group plus dispersed. And here you can have, like, we are co-located in this room, and then we have people who are dispersed, meaning that they are remote or maybe they're in other buildings. And so the challenge of this type of working adds a lot of complexity to our scientific collaboration. And so we can overcome this by being very thoughtful about our technology and about our communication. And also by having meetings like this. Okay, so now, well, I can ask if you have any questions at this point. Otherwise, I was going to spend a little time talking about these hybrid and virtual collaborations, but I won't spend too much time because I already know that you're very expert in this area. So let's look at what influences collaboration. So actually, Professor Nakajima already mentioned the ECP panel series. This was where we met. And so we have these resources available for anyone online. We have at least 15 different videos now on strategies for remote work. And I encourage you to visit this if you would like. And if you ever have any questions, I'm happy to answer any questions that you may have about remote work. Also, some of the factors that influence collaboration. I think that you have experts here, so we don't have to spend a lot of time here on this particular slide. I think the message that I would like to take away from this particular slide here is that the challenges are both social and technical. And it can be very, very complex. It adds a layer of complexity to any type of scientific engagement. And of course, when we build virtual and team culture, across our scientific collaborations, then there are certain best practices that we can use. I think that probably, honestly, the most important artifact for me of a lot of the remote work has been that now we actually have recordings and we have documentation, whereas before with in-person meetings, if you missed the meeting, you missed everything. And so years ago, when I was working with Fraunhofer Institute, we worked on a project called Tower, Theater of Work Enabling Relationships, Tower. And in that European project was about context-aware computing. And the most important findings was for our team were that if you have the ability to show someone who hasn't been at a meeting, if they have the ability to watch a video or to look at documentation, then they can be caught up very quickly. And so one of the things we did at that time was we visualized a repository for people who had missed some of the work that had gone on. If someone went on vacation, for example, and returned from vacation, then they could see everything that was happening. And so I see this happening again now with our tools. We were working with 3D tools, but these tools that we use today, Zoom, Teams, they're getting very good. And I think that this is going to be very good for our productivity. The challenge we have, however, is how to foster creativity. And so this is actually a research problem. I think about this a lot. How do we actually foster creativity? How do we replicate the conversations that happen at the whiteboard or around the water cooler? How can we incentivize impromptu discussions? And so one of the ways that we try to incentivize creativity and also software sustainability and software productivity at the same time is through the use of a tool that we've developed on our team for the exascale computing project called PSIP. And this is productivity and sustainability improvement planning. And the idea of PSIP is threefold. We have a suite of tools to allow people to scan the repository, data mine the repository to better understand what their code, what gaps they may have in their code where they need to do some improvement. We also have a self-assessment, which is, I have a representation here of a web-based self-assessment. The team will use this together to identify, actually, to better understand the common picture that the team has. And then the third point is we also offer progress tracking cards. So here for this Rate Your Project, and you can go to this Rate Your Project and do a self-assessment. We use this with teams to look at the software engineering. So the team together looks at the software engineering and they each use this assessment individually. And then they each have spider diagrams that show which parts of their code they feel they need to improve the most. But what usually happens is that each team member has a different idea. So we use this particular method with HDF5, the HDF5 group. And every developer had a different idea of what needed to be improved. And so this is really a communication tool to allow the team to better understand and come to a consensus about what they would like to do together. And so this is how we've used this with teams, and I'm happy to show you how to use this for your teams. After a self-assessment, we actually do a progress tracking card. And the progress tracking card, it has been motivated by Kanban. Are you familiar with Kanban cards? So a Kanban card is a checklist, but a progress tracking card is not a checklist. It is actually a card where you articulate your goal. And so the topic of the card is the title. The target is what practice you want to improve. What do you want to change? And then you write a user story. And then we have different stages of the card. So 0 is my initial state. Where am I starting? Stage 4 is my desired state. Where do I want to end? And then in between are the different stages to get there. And I'll show you an example. So this is an example for continuous integration. And we did create these cards actually with the HDF5 team. So they have some progress tracking cards that they used. And they used the progress tracking card after created to communicate their goals to other teams and each other. So in stage 0, we see here that in this example, regression and unit tests exist, but they're only run when requested by a developer. So the team has written what their state is at that time of writing the card. And then they move to number 5 and they write, okay, where do we want to end? What will be our best condition? So the best condition for this team is a mechanism and policy exists to integrate the code without passing tests in rare circumstances. So this is the goal that the team would like to reach. In the middle, 1 through 4, now the team sets other goals. So the first goal is that a test is run automatically according to a policy. So what does this mean? This is not a checklist. This means, if you can see the way that this is written in English, it's saying that it already happened. It's in the past. So by the time you reach stage 1, you already have tests that are automatically run, and you already have a team policy. So in between 0 and 1, what suggests is that you need to create a checklist for how to get a policy and how to automate your tests. And then the same for step 2. Reports are now generated and they're archived. So this builds on 1. You already have automated testing, you already have a policy. Now you have test reports that are generated, and you also have their archive. So now you also have documentation. On the third stage, now you also have reports that are posted to maintainers. And then you can see how you get to the 5th, okay? And so this is one example of a card for continuous integration. And we have many, many others in a catalog of progress tracking cards that you'll see the link for later. So the progress tracking card is actually a very easy tool to adopt because it is, I would say, it looks much like Kanban, and you can actually, we have markdown file. You can integrate this into your GitHub repository very easily. We have a tutorial on how to do that. It encourages reflection among the team members. You can use your progress tracking card every time your team meets. If you are using maybe a tool suite like Atlassian, and you have you're using Agile, and you meet for your Agile meetings, you can pull up your progress tracking card and make sure that you are still on target. And if your goals change, you don't have to worry, you just change your card. The idea is that the team uses the card to always see the common goal. And it also, this process can reveal differences in assumptions. Sometimes each person on the team has a different idea of the same thing. And so this type of process can illuminate that, which will help a team have consensus. And so I would like to conclude with the team of teams approach. And do I have a few more minutes? I think I end at 45, right? So I'll very quickly just want to say that I mentioned this. These slides are really meant to be shared. And so I won't say everything on the slides. I wanted you to have them so that you could look at them later and ask me questions later if needed. But the idea of this slide is that we have to think of it as it's an ecosystem. It's not necessarily it's an ecosystem that is thriving, that has things growing and changing at different rates, much like a garden. Heterogeneous code, people from different domain areas. So it is unlike other types of environments. And so because of that, we can think about different leadership styles of cultivating that garden. Also, when we scale from a small team to a large team, the biggest thing to think about is the shared consciousness, or to have that common goal that everyone knows what they're working toward. And I demonstrated how a progress tracking card can help us realize that shared and common goal in any type of scientific project. In this particular slide is also having a code team be able to execute. And so we already see that in GitHub, we know that developers make pull requests. There are reviews. I mean, this is a way that developers are executing in that network that I showed, which is part of Team of Teams. And so these developers are also working together to execute that code in a transparent way. And then having the ability for people working with diverse scientific teams to talk together. So if your codes are being used for energy, physics, or for space or other domain areas, if your engineers are working or developers are working with end users, if those developers have an opportunity to share information among each other, then that can accelerate the innovation and sustainability and reproducibility of the code, because the experts are sharing information and they might be encountering problems and challenges at different rates. And so they can actually help each other. And so this is, of course, the team of teams idea that we have been working on in the exascale computing project. And I hope that some of these ideas will apply to your smaller teams or your larger teams. There are many cross-cultural challenges as well that I didn't have a chance to talk about today, but I'm happy to do that. And so I would really like to acknowledge the IDEAS ECP team and all the collaborators. I would like to acknowledge our L3, Dr. Osni Marcus, and the Office of Science for the Department of Energy that has supported this work. And so here I have some links for you to go to some of the other resources in my presentation. And there are some more resources for you later in this slide deck that you can look at with many, many more links. So I thank you very much for your attention. Arigatou gozaimasu.
Okay, so next topic is about the parallel eigensolvers based on minimization strategy for massively parallel GPU system.
I was not expecting that you would be very much interested in ECP related things. So that's the reason that I was still working on my presentation. This one is ready. So, but as I said, I would be happy to share my slides that will be presenting on Wednesday, or talk to you some other time about ECP, a summary. So this is basically a talk that I presented last week at IKEM, Waseda University. I added a few more slides, changed a few things. And this joint work with Tom Popovich, Mauro Delbena, and Andrew Cunning, my colleagues there at the University of Berkeley Lab in California. And with funding from the SciDac Fast Math Institute. So why are we doing this? We started actually looking into this some years ago. We are targeting eigenvalue problems in electronic structure calculations. These are problems basically related with the wave equation or the Schrodinger equation. There is one, and we are doing this, interested in this problem, because if you look at this pie chart in the right corner, bottom, that's basically the workload of one of the systems that we had at NERSC Cori that I think Kengo mentioned before. This chart part is not new, but I think it reflects the workload that we still have we have these days on permuter. Basically, 1/4, 25% of all that machine was used to solve a specific kind of problem related to the electronic structure of materials, or using what we have in the left, the density functional theory. And that implies the solution of an eigenvalue problem. Okay, 1/4 the machine. Basically, what you have, DFT, I'm not a physicist, so I can go quickly through it. So if we're solving the wave equation, Schrodinger's equation, that's a very high cost, because I think it's even, maybe, if I don't remember, exponential, I think. But it's a very high cost to solve it. You cannot solve it explicitly, except for the hydrogen atom. Something bigger than the hydrogen, you cannot do it. Right? So basically, you have to do, then there are some approximations that you map a system with lots of equation involving lots of electrons into an equation with one electron. And then there's a way to put them together. Basically, what you have in this cartoon, then you start with an initial guess for the wave equation. You calculate a density that's based on the probability the electrons are going to be in certain parts of your system. You have to update the Hamiltonian that's defined in blue below. That leads to an eigenvalue problem that you solve, and you keep iterating using the solutions, the eigenvectors, to calculate a new density, right, or the electron distribution, until there are small changes between one iteration and the next one. Normally, what you do here, you discretize the solutions, the waves, the eigenvectors using some bases. Could be finite differences, could be Gaussians, could be Fourier, and that's what I'm gonna discuss a little bit in the upcoming slides. You could use direct methods for solving these eigenvalue problems, depending on how big the systems are. Things like implemented in algorithms like the ones implemented in Scale-IPAC, EigenEXA, which was developed at RIKEN, ELPA, that was developed in Germany. But for most cases, for the problems of interest, the problems are big. So then you have very big. So then you have to use some iterative method. And you are basically interested in computing only 2 to 10% of the smallest eigenvalues of the whole system. There are issues usually. The algorithms require some orthogonalization of the iterates, the vectors, because you need to keep them orthogonal. Otherwise, you may have instabilities when you are doing some other calculations in the physics. And then there are algorithms like Lanczos, Arnoldi, Jacobi-Davidson that could be used. So some years back, and we started looking to, instead of solving an eigenvalue problem per se, how to cast that problem in terms of a minimization problem. And this is what the physicists like, because you always get a system, a molecule, or is stable when you have the energy in a minimum state. So then that's the reason that some physicists or chemists, they don't think much in terms of perhaps an eigenvalue problem, but more into a minimization problem, right? Because the minimum of energy. So there are different ways of doing this. You could use what is called a constrained iterative CG, conjugate grid-based Eigensolver. That's the standard approach. And there, what you have in red, that's basically what I have to do. You take a set of vectors that you are iterating with, you multiply it by the Hamiltonian, by the vectors, you get a small matrix, and you're trying to compute the trace, which is the sum of the eigenvalues of that matrix, okay? You try to minimize that, keeping that orthogonality, vectors transpose times vectors goal identity. Here I'm using a real notation. It's usually in complex plan. So then at some point you have to do some reorthogonalization. The matrices, the dimensions can vary from 100,000 to millions. That's the size of the Hamiltonian. These operations involve a matrix, the Hamiltonian on the vectors there, the eigenvectors. Usually scale well because you have to perform matrix vector operations. But then the orthogonalization step that I mentioned, that doesn't works well because you are dealing with a small problems. As an alternative, you can remove the orthogonality constraint. That's what we call constraint iterative CG. And then that's the second equation there in red. You are basically changing the bases. You are not solving the trace of the. You are computing the tracing of another matrix. They're using a change of coordinates. You can see that there is the inverse of that matrix S-1 that we need to compute, but actually we don't need to compute it explicitly. We can approximate it by the first order of Newton approximation there. Taylor series, rather, the first term of Taylor. You could use higher degrees, but it doesn't give you much. So the first term of the Taylor is enough. you can show that the two functionals that you have for the constraint and constraint are the same, that lead to the same, to a minimum when they converge. You don't need to perform operations in a smaller matrix. And then, of course, the convergence properties are different. But we have you have more computations. In particular, so in the right, there is that little cartoon there. So it's basically how CG is used to minimize the problem. There are references there that I give as well. And in this minimization, there is a line search. And for that line search, you need this gradient that involves more computations than the constrained CG. What is the idea here? The idea is, since these days, people say that computations are free, the idea is to perform more computations, but saving communications. That's the idea behind this unconstrained. So previous work, this is what we did 4 or 5 years ago. We used CP2K, it's a quantum chemistry and solid states package. It uses a mix of DFT that I mentioned before, that's implemented using Gaussian, and plane wave-based approaches. What does that mean? It means that the matrices that you get are have a block structure. They're sparse with block structures. On the other hand, you have to compute to solve a generalized eigenvalue problem of that Hamiltonian times C equal to eigenvalues, right? Or C times E. And S is called S is called the overlap matrix, and E is the solved eigenvalues. We did some tests on a Coria machine that we had at NERSC that I think was similar to the machine that you had here University of Tokyo. And we basically at the time focused on the the KNL nodes using hybrid MPI plus OpenMP and using all the latest libraries that we could that we had at the time, MKL, ELPA, and others. We had to implement some novel preconditioners, and we could show we could perform tests using up to 230,000 cores on that machine. And we go here in this figure at the bottom right, that's for the molecule, the water molecule. And you can see some very good strong scaling for a molecule with 2,000, with a system rather of 2,048 molecules of water. Not so well for a larger molecule, and not so well for a smaller, but for a molecule of that size, we got strong scaling. And we had a paper published 4 years ago already on the ICPP conference in Kyoto. Time goes fast. Now, so that was a Gaussian basis. And now we are dealing or working on the plane wave basis per se. Okay, so that then leads to density matrices. So we are not discussing the pros and cons of those bases, Gaussian versus plane waves. Physicists sometimes prefer one versus the other. We are not discussing that. We are interested in understanding the performance of the algorithms, in particular the minimization approach, using either. There are a number of frameworks which and when we're doing this, the plane wave basis, basically we're going to use a Fourier discretization, and then you have to do some fast Fourier transforms for that as a building block. A number of frameworks, CP2K is a code that I mentioned before. There is another called QBox, IQ, VASP, that's perhaps very famous, but VASP is not, VASP is a proprietary, you have to pay for it. And Quantum Express, which is an open source code. So what we have noticed is that for all these different frameworks, FFT becomes non-trivial if you want to compare algorithms and different implementations. There are different implementations of Eigensolvers with different requirements for the Fourier. And it's another thing, it's hard to implement and target GPU or accelerators. So this is what we have looking at, and that's the reason that we started looking into strictly CPUs with that machine, the KNL hardware. And now you are seeing the impact of GPUs on this, in particular on the FFT, and also the linear algebra as we've seen. In these two cartoons at the bottom just show what the Gaussian discrete bases are versus Fourier. Fourier basically leads you to, in this case, ellipsoidal in 3D that you have to map in 2Ds or even in 2Ds, basically, projections on those planes. What we have done, actually, I'm going to give the reference in the next slide. We have developed, one of my collaborators there have developed a simple API for FFTs, which basically takes your input, discretizes it in the way you have in your problem, and you have to describe how you want your output, and then you create the FFT that's going to do that for your application. And you might ask, why, why don't you use packages for FFTs that are available out there already, like FFTW or even NVIDIA FFT? Because they don't give us the flexibility that we need for the FFT that we want to do for plane waves. So that's the reason. And they don't give the performance even because they're perhaps implementations of fast Fourier that are not target for materials. Okay. And with this, and this was a presentation that you see in blue that was Tom, my collaborator, presented. That it was parallel sessions. I was talking about the eigenvalues, and he was talking about the FFTs. So basically, he developed this API in blue there, that piece of the puzzle, that you could use other libraries for pieces of the computations, like FFTX, which is an FFT library developed with funding from the ACP, Accessible Computing Project. You can also use features that implement in a GPU or NVIDIA, for example, or AMD. You could use those, but as part of this calculations used by this idea of creating tasks for the FFT, performing tasks as part of the solution, or using the tasks provided by NVIDIA or AMD. Or you could use also MPI, plus in the sense to communicate from CPUs to GPUs and so forth. So with this, we have seen that we can achieve improvement in performance to do the FFTs that are required in the applications, materials, electronic structural calculations that are interested. If you'd like to know more how this is done, I would suggest to contact Tom. He's would be happy to answer questions. What is the performance of this? We have performed some experiments on Permuter, which is a machine there that we have a National Energy Research Center Computing Center, NERSC, where we compare DFT density. We are computed. That's again the density functional theory of plane waves, right? So do FFTs there, and there we have three implementations. One in blue is so the y-axis is execution time in microseconds, log scale, with a number of MPIs ranging from 8 to 4096. Plane wave is 64 because you can define for the physics, in order to keep the symmetry, you have to define the FFTs on a sphere. So the real, we are computing 2048 bands or eigenfunctions as physicists call bands. So then again, in blue, that's an implementation that used a CPU-based implementation using MPI, right? And actually OpenMP. We're using one MPI per node and then OpenMP on the node. So you can see the performance that you get. It scales well. But then if you move to the GPUs, and then you are in yellow, you have an implementation using MPI plus CUDA. It's 3 times faster than the execution compared to CPU. And if you use, in red now, if you use a GPU-based implementation with NVIDIA, that communication between the GPUs without going through the CPUs, you get an improvement in performance. It scales well to 2024 MPI ranks After that, there's a little more work there that I think we need to do. One thing that it's interesting here is that we don't do any additional parallelism below 108 MPI ranks, but above that we have to do, otherwise we would have code nodes that would stay idle. So we need to introduce another level of parallelism in the vectors in those two bands there in order to keep everything busy. So then this permuter is an ASE, as I said, a machine that has AMD plus NVIDIA. Right? What about Frontier? Frontier is the first exascale computer, right? I guess, at least using floating point operations at Oak Ridge Leadership Computing Facility. And for this one, is a system of the similar dimensions like the one before. And here we have two implementations. One is used in red, again, GPU using MPI plus HIP version 0, which is the, well, here we are talking about AMD's, that's the EPIC, plus the AMD accelerators. They don't call GPUs, right? It's the AMD accelerator. So then that HIP is, of course, then for those accelerators, that kind of accelerator. From version 0, from version 1, you can see that there is a reasonable gain of performance there. Maybe what? I don't know, it's a logarithmic scale, maybe 3 times faster or more from those two versions of a HIP, okay? And again, if we go above 128 MPI ranks, we introduce another level of parallelism. So all cores are busy, okay? So that was about the FFT. What about the linear algebra that are using most solvers, linear iterative solvers? Here, we can talk about Jacobi-Davidson, this project PCG, project precondition CG, conjugate gradient, that I'm the one we have been focusing, constrained and unconstrained. You are doing in blue, that's what you have. Matrix time a block of vectors, that's the FFT. In other parts of the algorithm, you have kind of rectangular matrix times a rectangular matrix or rectangular times a square, or in the algorithms that you need to keep orthogonality, you are doing something like Koleski QR on a small matrix. That's the part in dark blue there at the bottom. And how do these things scale? How do these things scale? So let's take a look here at the plane wave. When you are doing that rectangular matrix time rectangular matrix, this you might think, well, this is a solved problem. We don't have to think much about it. If we use the libraries again, that in this case, that's permuter that we have on NVIDIA, I mean, provided by NVIDIA. So if you use CPUs only, let's put aside the GPUs for a while. If you use the CPU only, if you use the two different implementations for matrix, rectangular times rectangular, using the summa implementation or the canon, you see that implementation, you can see that they scale up to 200, roughly equally, up to 256 MPI ranks. After that, you can see that the canon implementation outperforms summa. There is a little, kind of summa starts kind of flattening a little bit there while you get a good scaling for canon. There's a difference in those two implementations. Now, if you take a look at GPUs, that's the graph to the right. Again, this is on permuter. So if you use a GPU-based implementation using summa and canon, the performances are not great. They're kind of flat. That's the red and the yellow curves. They are flat up to 64, and they start scaling a little bit, but not much. If you use the communication among the GPUs, the NACCL, things improve, but still you have a part of the curve there that's kind of flat and then starts scaling. So what does that mean? That if we still have room there for improving the linear algebra computations, even on the hardware that we have right now. And this is important. This is important for those simulations, that we have in materials. If you want to speed up really, the calculations. And here again, MPI ranks from 8 to, well, in this case, from 8 to 124. So this is the work that we have been doing now. As again, we started some years ago there, focusing on on Gaussian basis, because that's the code we're looking at. Now we were looking into plane wave-based DFTs, and with the, doing this on a GPU-based systems, we have opportunities there. We are now facing problems. We are seeing things that we could not anticipate, and they are sometimes counterintuitive. We started to look into a code for FT that's called QBox, but that code, we found that was not so easy to implement certain things. In particular, FFT, as I mentioned before, becomes non-trivial for algorithm comparison purposes. We have decided to move to Quantum Espresso, use this as reference, which we think is a more flexible framework where we can try different implementations of FFT and also the linear algebra. And with that, Quantum Espresso already has the set of algorithms implemented there, iterative algorithms like Jacob-Davidson, PPCG, as I mentioned before. There is one algorithm called the DIS that is not, I think I am more in this numerical linear algebra community. I don't think DIS have been used at all in this community. It's more the physicists that have paid attention to this clever algorithm. Well, the ones in blue is the ones that we have implemented the Quantum Espresso, and we are now in a better position of doing really the comparisons on these architectures like Permuter and Frontier that have this hybrid CPUs and GPUs to see really what kind of algorithm is more appropriate given the systems of electronic systems of interest. Thank you.
Okay, so let's start the next part. And in the second part, we have 3 talks by my colleagues. And the first one is Mitsuaki Kawamura from Data Science Research Divisions. So he's a specialist of the material science. And title of his talk is Data Accumulation in Advanced Research Infrastructure for Materials. So please start.
So thank you for your introduction, and thank you for inviting this ASE seminar, me and Professor Suzumura. So my original research field is quantum mechanical simulation, just like explained, presented by Professor Marquez. But today I'll talk about totally different topics for related to my project. So the entitled to Data Accumulation in Advanced Research Infrastructure for Materials. So this is, in short, ARIM project. So my collaborator is Masato Shihanai and Professor Toyotaro Suzumura. So outline of my talk is like this. First, I talk about the motivation of why we need to construct the IoT, the double system to accumulate the data for material science, and details of this system is explained in here. And then I briefly talk about the future of usage of this system and summarize. Okay, the overall motivation of ARIM project is to investigate materials from the microscopic pictures. So to this purpose, we need, for example, we simulate quantum mechanically by solving some Schrödinger equations, or just using some spectroscopies like photo emissions. And to accelerate such a material science research by sharing some experimental equipment in each university like University of Tokyo or institute like NIMS in Tsukuba, so National Institute for Material Science. So this kind of equipment is sometimes very expensive. And it's better to own by sharing some inter-college project. So in ARIM project, we share, for example, the electronic microscope to measure the surface structure, or X-ray diffractometer to see the crystalline patterns, or for other purpose, the clean room to fabricate some like nanoscale circuits or including some mechanical system, MEMS. So to share such a experimental equipment to accelerate science, material science research. And one goal, there are several goals for this project, but one goal related to our ITC ALIM part, division, is to accumulate the user data and utilize that for later researches like material informatics. So to encourage this data accumulation, we have some plan. So for example, discounts the usage fee for data providing users. So some people want to use some private system, but for the users to publish the data can get some discount for the usage fee. And also providing some free use the data storage for users. But there is one problem for this purpose, that this is the PC, this one, operating some equipment like microscope. So this is the JEOL microscope, is typically standalone. So this is not connected to the internet because the OS of this system, PCs, is sometimes legacy because they cannot be updated because of the driver, software limited. Such a driver is not updated by makers. So the typical lifetime of this kind of equipment is very long, more than 10 years. So this PC is standalone. And to transfer the experimental measurement data to their users on PC or moreover to the public storage, we need some USB flash memory or more secure
Windows 7
way is to burn some DVD disk. So this is a very complicated and sometimes very time-consuming step. So we need to bypass this kind of complicated procedure. So for this purpose, we constructed some laboratory information management system. So in short, so this kind of research is called LIMS, development of LIMS. So the purpose of LIMS is, for example, the scheduling, machine time scheduling or data transfers, or constructing some remote control infrastructures. So conventional LIMS system is for the small system or the same kind of machines is operated in the LIMS. But in our case, there are many kind of machines, such as microscope or XPS or X-ray diffractometers or clean room nanofabricating system. So a little different for some for the previous LIMS studies. And so also the system or PC system is very legacy. So this is a limitation for our case. Okay, so our purpose is connect the standalone PCs to our data storage and then publish by using NIMS RDE, NIMS public data repository. So final goal is to bring the data, all data to the NIMS public repository. Okay, so there are several previous works for the LIMS. The system structure is like this. Our system structure is like this. So there are several facility or experimental equipment in our campus and connect their PC to some simple USB IoT device. And this data transfer is one way, always one way. There is no backward transformation for some malware or some virus. So this IoT device blocks such a backward transformation. So the data transfer is always one way to some MDX. So I'll explain data. MDX data storage. Then finally we publish to the some things to the data centers. Or in future we use a supercomputer to analyze such as big data. Okay, so the developer is main developer is not me. Dr. Hanai in ITC. He developed almost all systems. And also from the part of engineering, Yo Igarashi provide some insight. Okay. So this part, MDX cloud part is we use a MDX server. So this is a kind of different just like the Amazon cloud. So but cheaper for academic users. So conventionally, the supercomputer has a very nice performance, but not so flexible because we cannot use the supercomputer as a root. On the other hand, for the local server, by purchasing some PC clusters, we can operate this as a root users and freely install some softwares. But it's not scalable. So it's difficult to extend this system for large scale or connect to some fast network system. So on the other hand, MDX is in the middle position of these two kind of computational resource. It has a high performance computational resources with virtual machines. Each virtual machine has almost same performance for one node of supercomputers and easily control or operate change the configuration by the root permission. And also the network connection is very fast. And this MDX operation has been started in this April, a very new system, and having CPU nodes and GPU nodes, also the large scale storage system. And not only academic usage, also the collaborative study is welcome. And this system is operated by 9 universities and 2 institutes. And the paper is already published. So the schematic illustration of the system setting of MDX is like this. We have 368 CPU server and 40 GPU servers and large scale storage system, fast storage system. And this S3 object storage system is directly connected to the web internet. The good point of the VM in MDX is the flexibility and the isolation and portability. So we can port our own PC configuration easily to the MDX by sending ISO image. Or also we can construct private network. Flexibility. Okay, so, and in addition to the MDX system, we have additional storage in the next to the MDX system. So physically, this ARIM system is next to the MDX in here. So we have 3 petabytes, 3000 terabyte system storage and high-speed access to MDX. This connection is very fast. And also we have the easy to use web front end like Dropbox. And the data transfer from the equipment is done by like this. We constructed this kind of small IoT device by using Raspberry Pi and USB cable. And this system, this IoT, this device can be seen as a USB flash memory from this PC. But in fact, this one is connected to the network and directly port to MDX. But the backward transformation is disabled, is blocked. So in future, we plan to analyze such experimental data in MDX on time, real time. So but we have many plans to utilize this. Okay, so the real picture is like this. We already constructed 3 pieces of this system and set up 15 of these to the electronic microscope in our Asano campus, next to the Hongo campus. And also Dr. Hanai constructed some useful web browser and in web front end can be seen in web browser like this. You can easily check the microscope image from this. Also launch some Jupyter Hub and perform some analyzation by using R, Python, or VS Code. And the future plan, so it's a very fancy future plan. It's like this. So to construct the permanent, high power permanent magnet or tough materials, large scale, stable and large capacity battery, or some electronic device, solar cells with less toxic atoms or cheap common metals. For this purpose, so we first synthesize them and measure with some large scale experimental system and change the condition and retry and turn this cycle. But in future, we predict such an optimal condition from the big data that we accumulated, or experimental or virtual screening with quantum mechanical simulation by using our supercomputer Wisteria or Oak Forest Parks too. Okay, this is a summary. So we constructed new Linux system scoping focus on our ARIM usage. And this is already working. So thank you for listening. That's all.
Okay. Thank you very much, Kamara-san.
Thank you very much. Nakajima-sensei.
Okay, so next talk is by Shinji Sumimoto, and so he will talk about the system-wide communication library to couple multiple MPI programs using H3 OpenSys WaitIO.
Thank you for your introduction. I'm going to talk about some of this title. Unfortunately, this topic is almost same as maybe last week in the mini symposium. I'm sorry about that. So here's the outline of my talk. I'm first talk about the heterogeneous coupling computing using some H3 open video project. then going at a little brief overview of H3 OpenACC WaitIO. It's a design and implementation and evaluation. Firstly, we are going as a project to the H3 OpenBDEC. That's the innovation software platform for integration, simulation, data, and learning on the BDEC system. So we are started in 2015. There are three kinds of innovations. One is new principal numerical analysis of adaptive precision and automatic tuning, accuracy, and verification. And second, maybe a main topic is hierarchical data-driven approach based on the machine learning. And third topic is software for utility for heterogeneous environment such as with a BDEC server. So this talk is around some third topics. So the target system with the BDEC one, the operator may start in May 2021. It is 31 petaflops and 8 petabytes made of it. And there are two types of node groups. One is a simulation node. It's called by Odyssey. It's a commercial version of Fugaku and which is Prime HPC FX1000. It's an ARM CPU. And around 26 petaflops and 7,600 nodes, and top of the interconnect and general CPU and high bandwidth memory. And second node is a data learning node called by Accuracy. It's a data analysis for machine learning for use, and it consists of Intel Xeon Ice Lake 2-socket and 8 NVIDIA V100. It's around 7.6. These two kinds of Odyssey and Accuracy is connected by a high bandwidth InfiniBand HDR. It's 2 terabytes per second, and also they are connected by two kinds of shared file system. One is shared file system based on SD. SFS and shared file system. It's 80 based and 26 petabyte and 500 gigabyte per second. Another one is a SSD based called fast file system. It's 1 petabyte but 1 terabyte per second. It's a very high bandwidth. So this kind of system. So using this system, we are going to some S plus D plus layer. So then go at the WaitIO. It is the aim to develop and realize heterogeneous coupling computing. I talking about some background. With the spread of the higher scale computing system, maybe HPC application have become able to solve more practical problems. For example, example one is some real-time simulation with various kinds of sensor data and estimate the future. A second example is improving correction accuracy by assimilating correction results and real-time data. And the example three is using computer simulation results as machine learning data and doing simulation using infinite computation. So this is kind of application I talk about. To realize such a thing, so we believe that the fusion of multiple applications is the key with the simulation, data processing, and machine learning. That is because we are progressing some of heterogeneous coupling computing. That's why maybe WaitIO is a key communication component to realize such our goals. So for example, real-time heterogeneous coupling computing using WaitIO on a VSB. Here is a real-time earthquake simulation. In Japan, JDX Center is called by Jishin absorption data of the observation coming. After the real-time communication, we got some of observation data maybe per 1 second, maybe 1 second, and so getting data from the node Accuracy. And there in Accuracy, then goes a filter. Because some observation is a lot of some sensor and some sensor positions. So we are filtering some limited data per second. So again, goes to some filtering data is going to send to the Odyssey, And in the Odyssey, we can use ask estimation in the size of 3D open SWF and DF and data assimilation. And then go to back some data from to the accuracy and with output and movies. For each one. Another thing is simulation is a Python approach and coupling of H3 open utility MPI. This is maybe another highly functional coupler developed by maybe Dr. Arakasan. And in this case, maybe we have some example. This is some of HPC application, for example, Nikon in the Odyssey, and some accuracy using some of using some machine learning application, maybe using some Python and PyTorch, and this kind of coupling. And if some Nikon call the result and send the data to the accuracy, and they go to some accuracy in the, for example, using some making some aggregation model, surrogate model, and visualization and statistics by connecting two kind of application. And the other things are usually a coupling operation using a shared data among the application using a file. And that time, so that kind of application is easy to translate to using a WaitIO. For example, this is a couple of sample coupling program using file coupling to WaitIO coupling. For example, this is a very simple code, code 1 and code 2 and code 3. And code 1 outputs some calculation is point source calculation. Is somewhere this is a program 3D unsteady heat transfer program with the infinite element method using the iterative linear slow burst. And some code 1 outputs some of point of source calculation. That's a S1.out, and then goes to some code 2 and code 2 reads some of the S1.out and calculate. And the code 3 also using some output data of the code 2 and some of the file and S3 out. And then with such kind of data also, I took some example of the data. The another is this is heterogeneous corporate composition by WaitIO. This is also a toy program in the GeoFM Cube toy program. Usually some GeoFM uses this kind of shape in all a single system. However, using a WaitIO, you can divide this kind of shape to half. And for example, maybe one part of calculated by GPU system, and the other part of it is calculated by CPU. You can write such kind of program by using some WaitIO. So I talk about some next topics. How the heterogeneous coupling computing issue and the requirement. The issue is no standard communication protocol between systems because two kinds of systems very different. MPI, interconnect, something different. So you system you can use MPI and such a thing. But the two kinds of different systems makes it difficult to connect. So the issue is no standard communication protocol between the systems. That's the problem. So one solution, the developing communication library, that is because we developed by H3 OpenACC WaitIO. So what is the requirement of the communication requirements? So one is a very important thing, operating on a heterogeneous hardware and software. Because of multiple applications on different machines, highly tuned for each machine. So we do such an application as it is unconnected some different way. That is a very strategic way I think about. So that's a kind of multiple application on different kind of nodes and combined, and also applicable to heterogeneous hardware and software. That is required. And another thing is combining multiple application groups with flexible. But it is corrected by easy to adapt that. So software modification should be minimum and also close to the program model standard and should be coexist with other system software. That's the problem. So we developed WaitIO using a socket communication and also file communication, shared file communication. Two kind of systems, but both maybe some of them can be used. So how is some distributed? So WaitIO and file dedicated interface. It's supporting different kind of processors and different kind of interconnect, and also a different kind of MPIs. Its codec can be overview. And also possible with MPI and other system software. It doesn't, it's a project standard, so even if in Windows, you can use that WaitIO. And second thing is providing API that conforms the MPI specification. Is related conformance. MPI is very standard. And also, second is operating minimum, maybe computer resource for 10,000 process. And how to define some WaitIO? Maybe some WaitIO hybrid is a combination of WaitIO socket and WaitIO file. So WaitIO file is using a shared file system using project schematics. For example, FFs and raster file system. And hybrid is usually maybe socket communication is very faster than latency in the shared file system. So with IO user for short message using a socket and maybe a longer message using a file. So here is the API of the WaitIO. Each application defined as parallel break. So in that case, there are maybe three kind of system by running the three MPI program. And this is defined maybe two kind of steps, parallel break ID 0 and 1 and 3. And when you come together in the three kind of application and selected any selection of the process you can want. So creating some WaitIO group, then communication start. So API is very simple. Maybe using some MPI, I send, I receive, wait, that's only. But no data types. And different some creating group functions and some of miscellaneous functions. So actually, my WaitIO specification does not have MPI data types. So sometimes it's difficult to translate MPI program to WaitIO program. So we also prepare some WaitIO MPI conversion library. It has some data types. So WaitIO using this application, you can translate so MPI applications to WaitIO almost mechanically replacing some of it. For example, some of WaitIO I'm saying adding only some WaitIO underscore prefix. That's only data type also. And I'm some here topics. Like here some. So how this is maybe a shared file system. So this is the original program, code 1. This is a Python program and different MPI that's not defined. So open some S1 file and some these some initial file, then go to some S1 data. This is our output file. And some doing some of calculation and write. This is the original code. So how do you change for WaitIO? WaitIO converting some open and read write to I send, I receive, I wait. In that case, some of the WaitIO structure maybe added some status and request and adding in header file and allocate some data file and some code and WaitIO create universe pivot. This function is just each calculation rank 1 is connected by using a WaitIO group. So in this case, some application number code 1 is rank 0 on the WaitIO, and code 2 rank 1 and code 3 rank 2. And this is maybe open is not good and stayed, and this is code 1 output data, but code S1 dot out is by read by code 2 and code 3. So we can do a destination rank number 1 and 2 and the same I send TTT and source and I send and finally WaitIO MPI WaitIO. That's only. Also It is, I tried to some P-hit3 provided Nakajima sensei, and this converted to the example. That's a very easy case. Some other some header file and some allocation, some requests, and that after that, almost for example, MPI send the prefix weight underscore and also data type also. This is also same and very easy and mechanically converter. So it's for me. Some implementation weight socket and file. It's a communication using socket and file, and some commission protocol is some under the 128 byte user EGA protocol. After that, over the 128 byte using random protocol. And also commission processing in the when weight is called. And also socket commission is using a project socket and the next equal function and calling some WaitIO init, some they are gathering some form of parallel information, for example, IP address and port, and gathering into making group. And all the file implementation and realize file code same as WaitIO socket. Because some WaitIO socket and file only a Linux and maybe read and write system code. If I use such another commission library, it depends some dependency and sometimes cannot run. So because I am a simple project read-write system code. And I don't have a time, so I skip there. So evaluation of WaitIO socket, it's a ping-pong communication boundary with multiple stream. So here's a WaitIO and WaitIO socket ping-pong boundaries. Obviously, one knows accuracy one knows. This is a heterogeneous communication. And here's a message length, and y-axis shows a megabyte per second. And here's a row, increasing the number of the user, 2 nodes, and increase the number of process connection to the 2 nodes. In this case, this is some WaitIO socket, and this is a WaitIO file. In the socket is very limited to the 182 megabytes per second. However, using a WaitIO file, increase the number of connection. If you increase the bandwidth up to the 2 and 958 for a second. So because some limitation is GIO, this is FK1000 and what is a toxic interconnect. However, to communicate some accuracy, they are using some GIO. This is bottleneck to the communication. I skip that. So next is some WaitIO socket, and now is some if you use some research one user, you can use H3 OpenACC MP and WaitIO socket. That's since in maybe last June. So I'm some skip. Is that enough time? Almost there. So I took some evaluation of the application. It's a NICAM and aided application. That means some of the collection of some NICAM data use some of either use some machine learning to reduce that kind of thing. So, and this is a total identity and inter-energy and density of water vapor. And the framework of PyTorch method and 3-layer MLP. And here's the result. This is a comparison of the socket, file, and the hybrid. So this is the homogeneous, and this is heterogeneous. And the NICAM ADA process time. Here is socket, file, and hybrid. So you can see that some of possible some heterogeneous computing is faster than homogeneous computing and both sides. So here's a summary of our talk. Here I talk some of the application. And the future work, we are trying to apply the several applications, and some projects go on. And then going to some of I'm now developing a WaitIO valves that is used for InfiniBand and Rocky and Slingshot. Thank you very much.
Okay, so final talk is by Kazuya Yamazaki. He's a specialist of the atmospheric science. The title of his talk is Porting an Atmospheric Model to GPUs using OpenACC.
Okay. Thank you for the introduction. I'm Kazuya Yamazaki at the Information Technology Center at the University of Tokyo, and my primary research topic is weather, atmospheric science. So I use a weather climate model very often. So I ported one of the simulators to GPUs using the OpenACC technology, and introduce some modifications to the code, and managed to get some reasonable performance on A100 NVIDIA GPUs. Here, the latest supercomputer here in the University of Tokyo is called WaitIO VDX01, and it consists of two subclusters. One is mainly for simulations and is a CPU cluster, and the other is equipped with GPUs and is meant for data learning, data science and learning. But in the near future, we expect GPU-equipped machines to be dominant. So we have to do simulations in GPUs in near future, and we need to migrate from CPU. So I ported my weather climate model to GPUs using the OpenACC technology. And my model uses a framework called superparameterization. Basically, I use some global low-resolution model handling the atmospheric circulation of the entire Earth. And this low-resolution global model have a lot of vertical columns. Each of them are around 100 kilometers wide. And so this large number of vertical columns are linked in this superparameterization with many domains of high-resolution crowd-resolving model. This crowd-resolving high-resolution model takes care of clouds and other small-scale processes. And these high-resolution domains are two-dimensional. The atmosphere is three-dimensional, but here we reduced one axis to save some computational costs. And the horizontal boundary is periodic. This is not the case for in the actual atmosphere, but this saves the lateral boundary conditions. So in this setup, we can conduct the global simulation with high resolution, but less computational cost. And we can also very significantly reduce the MPI communications. And let me skip the details of the model, but basically we have a global component and the high resolution model component, and we have some communications between the two to synchronize the two components. However, the global component is very low resolution, and its calculation is very fast. So as for the computational cost, we can ignore this global component. And data communication is also very fast because it's not required very often. So we have to only exchange some small amount of data infrequently. So the only problem is the high resolution component. So we want to make this very fast. And the high resolution component is adapted from existing crowd resolving model developed by the Weekend Research Institute. This scale RM model handles three-dimensional atmosphere, but we need a lot of two-dimensional high resolution domains to implement this for the superparameterized model. So I hijacked the y-axis of the scale RM model and used it as the domain number. Here is shown as 248 to minimize the code modification required. And as I talked earlier, the only computationally heavy component is the high resolution component. And the global component is still on the CPUs and it's not refined. But anyway, here we concentrate on the crowd resolving component, this scalar component, and exclude the global component. So if you run some program on GPUs, you have to make sure that the data is consistent between the CPUs and GPUs. And on NVIDIA GPUs, we at least if you use OpenACC, you have two options. One is to use a unified memory technology, which automatically synchronizes the data. And the other is to explicitly handle the data using the data directives. And actually, there is already a very similar superparameterized model already ported to GPUs, published in 2021, and they use the unified memory technology. And however, they noted that the unified memory resulted in some significant initial latency, so they had to prefetch the data explicitly anyway. So the overall cost handling the data is not very different between the unified memory and explicit data directives for now. Anyway, I made sure that almost all the array operations happens on GPUs so that little host device data transfer occurs. And usually atmospheric models have very undesirable code structures for GPUs. One is this kind of loops. This is a horizontal loop spanning I and j, x and y dimensions, and we have a lot of processes, including subroutine calls and vertical loops. We have only two of them, and many of them are in actual atmospheric models because we have to handle many processes, including clouds and anything else. But if when I try to post this kind of code on GPUs using the OpenACC, it just didn't work. The parallelization was very limited due to register shortages and anything similar. So I had to modify the code and modify the subroutine to handle three-dimensional array instead of 1D, and got this outside of the loops, so it won't be called as often. And I modified the loops to three-dimensional simple ones to parallel them well. Another characteristic of atmospheric code is that hundreds of small kernels are in the one time step, and none of them occupy more than 5% of the total calculation time. So no kernel is dominant, and we have to make every kernel as fast as possible to get reasonable performance. So the typical kernel only runs for 20 microseconds. So the latency of the kernel launch and post-execution synchronization is non-negligible. So we do not want this kind of thing. We do not want to launch kernel synchronously, and instead I launched the kernel asynchronously in one queue to save the launch latencies. Let me skip this for today. So let's move on to the test configuration. We had some specific numbers or number of grids per CPU cores or GPUs, and we had multiple GPUs from NVIDIA and one CPU from the V0V01 ASE subcluster, and two types of Intel CPUs. And the performance here, the horizontal axis is the theoretical memory bandwidth of each subprocessor, and the vertical axis is the throughput of my model. For the radiative transfer scheme, this component has fewer large loops, so the kernel launch latencies and similar things are not as important as the whole simulation. So if we look at the left figure, the performance is nearly proportional to the theoretical memory bandwidth. Typically, all atmospheric models are highly bound by the memory access speed, so the performance is proportional to the memory bandwidth. However, if you look at the whole simulation, including many small kernels, we notice that the Intel CPUs have larger gigaflops compared to very small memory bandwidth. So I think that the latencies are small in Intel CPUs, and it performs well. And we have the NVIDIA GPUs. One is the H100, the latest generation GPU, and the other is the A100, previous generation GPUs, and the performance is modestly improved. And here in this figure, this red F indicates the Fujitsu's A64FX CPUs, and it looks as if the Fujitsu CPU is performing very bad. But it is not the case if you look at the power efficiency. This table shows the power consumption and the performance. And if you calculate the gigaflops per watt, then the A64FX CPU is actually performing more than twice as good as the Intel Xeon CPU. And the A100 GPU is even twice as power efficient as the A64FX CPU. Here I included the power consumption of the host GPUs for the GPU performance. I noticed something on H100 GPU, air-cooled GPU. This is the upper left figure is the power consumption as a function of the time. And even though the NVMe measurement of the power consumption captures the initial sharp jump of the power consumption, the measured power gradually increases for several minutes, and it increased by 40 watts. And this, the GPU clock rate was constant at the boost frequency. So even though the GPU was doing the same thing, the power consumption was increased by nearly 20%. And I believe this is because the temperature of the GPU increased. And I guess that this experiment was performed on air-cooled machine. So the GPU was got hot, and leakage current was increased, and so the power consumption was increased in gradually in time. So if we evaluate the power efficiency, then we have to make sure that the GPU temperature is steady and measure the later part of the simulation to carry out a good comparison. Here, I compared the power efficiency for the A100 previous generation GPU and the latest generation H100 GPU. The comparison is not exactly fair because the A100 is water cooled and the H100 is air cooled. Anyway, the performance per watt is 2.9 on A100 and 2.4 on H100. So the performance per watt of the latest generation H100 is not always better than A100. One of the reasons is that the H100 got hotter because it's air cooled, and so the comparison is not fair. Even if the GPU was water cooled, the performance would only increase by 20%, so the gigaflops per watt would be almost the same. This is probably because the memory bandwidth of H100 PCIe is not boosted that for the calculation capability. So the byte per flop is lower than the A100. And our model is very memory bound. So the H100 PCIe version that did not perform as good as expected. However, on another flavors of the H100 GPUs, faster memory equipped, they are equipped with faster memory, so we may see some better results. So to summarize, I ported weather climate model to GPUs using OpenACC and introduced some modifications. And the A100 achieved some better power efficiency, but the H100 GPU is not always better than the H100 because the byte per flop is lower than the H100, A100. And the Fujitsu A60FK seems to be slow, but very power efficient than the Intel CPU. That's it. Yeah, that's it for. Thank you.
Okay, thank you very much. And so this is the end of today's ASE seminar. And so thank you very much for very nice talks and also very exciting discussions. And I'd like to thank all speakers and the audience. And the next seminar, 44th, is next week, the same time. And if you are interested in, so please join us. Okay, thank you very much.